Okay, so today we will look at finish off the Muller matrix. I mean, the polarization algebra uh, that we started in the last class. Let me start sharing the window. So we will basically look at. Can you see my window? Yeah, can you see? Can you see it?
Yes, sir.
Yes, sir.
Yeah. Okay. So basically, we ended last class by defining the coherency matrix, and which is very important because in the treatment of polarization by the Jones algebra, it the effects of depolarization are not taken in. It is indeed the coherency matrix which is a more complete treatment of the polarization, and it sort of also allows one to measure whether light, a beam of light or whatever, whether light that is propagating, whether that actually has, what the information about polarization that is essentially much more apparent in the coherency matrix compared to the Jones matrix, which deals only with pure states. But then, of course, the much the most uh, uh, complete way, I would say, of dealing with polarization is using the Stokes-Muller approach, and that is what we are going to study today, look at today. And of course, once I finish this, we will actually ask Priyanuj and his friends to tell us about the Pancharatnam phase experiment that they had done, and just tell us a little about the Poincare sphere and how it is relatable to experiments and all that. But let us just start today then by the Stokes-Muller formalism. Interestingly, this the Stokes approach was developed far before the Jones approach, which is quite interesting because you tend to feel that that is a more the Jones thing is the more comparatively incomplete picture, but it was actually developed later by, as I said, I think I wrote last time, it was developed in the 40s by Dr. Jones, of course. But Robert Gabriel Stokes uh, actually developed this approach in 1852. Okay, this is much earlier than the pure state approach. Okay, of course, Muller, that is, so the Stokes vector is the equivalent of a Jones vector, but of course that incorporates depolarization as well. Uh, the equivalent of Jones matrices is actually the Muller matrix, and that again was developed later by I think it was Hans Muller around again in the 40s. So that period, which was actually witnessing real, I mean, revolutions in physics, also saw these things about light also were developed during that time, which is quite interesting. I mean, Stokes knew that intensity uh, actually revealed properties about polarization much earlier than the of course the coherency matrix treatment came along with the Jones treatment. So you can say that the Jones plus coherency matrix taken together is kind of equivalent of the Stokes treatment that was actually developed much more earlier. Okay, so I think most of you are familiar with the Stokes treatment. So you actually think of these parameters. They are entirely dependent. They are actually measurable experimentally. and they give you complete information about polarization properties of light. And so these are essentially the Stokes vectors are nothing but intensity based representation of polarization states, and they are sort of intimately related with the coherency matrix, as we shall just see. This is all pretty straightforward, so nothing very spectacularly complicated or anything of that sort. I think you're all familiar with this IQUV. So I is the total intensity. Q is uh, what is Q? Difference between vertical minus horizontal. Difference between vertical and horizontal. U is the difference between 45-degree polarized and 135-degree polarized, or it is the difference between 45 and minus 45. V is the difference between LCP and RCP, right? So if I write in terms of time averages, then this is EX star plus EY star. This is EX star minus EY EY star. This is EX EY star plus EX star, and this is I EX star minus EX EY star, right? So again, if I make this, in terms of intensities, if I directly write in terms of measurables or something, then one representation is if I just say that this is E0 x squared plus E0 y squared. This is E0 x squared minus E0 y squared. This one is 2 E0 x E0 y cos delta, and this is 2 E0 x E0 y sine delta. So this I will ask you to prove in, I think I will give you a short assignment today, very simple, but yeah, I think your previous assignment is due on Thursday or something, I guess. So I think I will give another short stuff, based on just this.
No, sir. The
Maybe
previous
for
assignment is
is
due
over,
tomorrow
or when
night.
is it? Tomorrow. Okay, whatever. Yeah. So then I will. This one will be due next Wednesday. So it's again a very short assignment. So by the way, so this one can write as IH plus IV. This is IH minus IV. This one we write as IP plus IM, and this one we write as IRCP minus ILCP. IL. So what are all these? I'll just write down. So IH is horizontally polarized. IV is vertically polarized. IP is linear polarization at plus 45 degrees. IM is linear polarization plus 135 degrees or minus 45 degrees. IR is RCP, and IL is LCP. Now, directly from here, I think it is okay. So we should also define some other quantities, which is again, these are, I think, see, I'm writing these, I think because these are important, very crucial for experimental measurements, experimental determination of polarization in light. You can quantify polarization of any type of light using, by these measurements of these parameters. So, right, so this degree of polarization is given by Q square plus U square plus V square by I. Degree of linear polarization is, of course, the linear component, which is Q square plus u square divided by I, and degree of circular polarization is simply v by I. So these are all things that I think should be clear about. But what I want you to, so one, yeah, okay. So now let's go step by step. So one, the moment I write this kind of notation, this is why I wrote this first. See, you can straight relate this with the coherency matrix, right? Because these are all nothing but elements of the coherency matrix, right? So in terms of coherency matrix, we can straight write down the Stokes vector matrix. We have S as very nicely phi xx plus yy, phi xx minus phi yy, phi xy plus phi yx, and I times phi yx minus phi xy. This is very interesting. And the reason that it's very interesting is we can now say that, we can sort of associate this, this thing that I wrote, I can actually write in terms of a matrix equation. And why this is important is that you can actually, so one can always see the whole thing of, in science we keep on making connections, right? So it is imperative that we have some kind of connection between all these treatments that we make. So the next step that I'm going to do is actually important because it will also help us associate later on. So we have somehow related the coherency matrix with the Stokes vector, and the coherency matrix, we remember, that was similar to the Jones thing, which is a 2 by 2 representation. So this was also like that, in the sense that you just need to measure the x and y states of light. That is fine, but you're the whole 2 by 2 treatment, we are kind of getting into the 4x1 treatment, the 4 by 4 treatment. So this next step that I'm going to write is useful because we are actually going to correlate the Jones and the Muller Jones matrix and the Muller matrix using the similar kind of approach. Okay, so what I'm going to say is that I'm going to write this as some A times this.
Sir, I have a question.
Yeah.
So,
Okay, so I've made a
first
mistake.
one
One
is,
second. One second.
yeah,
It is just let me just correct this. This is x y. Just let me correct this one minute. Just this x y by y x and phi y y. This is an a. Yeah. Oh, that's horrible. One minute. Yeah. Tell me.
sir. First thing
Uh,
is, why there is a plus in the third element?
this one. This one.
Yeah,
Yeah, because I'm saying, see, in terms of it is actually, so 135 is the same as cos 45, right? So I mean, minus of cos 45, na? So it's actually cos delta. Okay, the difference is actually, so that's what I said. This is IP plus IM, where it is actually plus 135. So if I write vertical minus horizontal, this is IP plus IM I wrote. This is the same as IP minus I of minus P. You understand? So it is actually 45 minus minus 45. So minus 45 is the same as plus 135. So those are the same orientations, right? I mean, if
okay.
you define, that is what you do. Yeah. Other question?
And how are we representing IP by this expectation of EX and EY star?
Expectation nahi. This is time average.
At a time average, yeah.
Huh.
That is expected with respect to time. That is fine. No,
This
I'm asking why, how are we representing that in that way?
this one.
IP by EX EY star?
So this is basically coming from here, no? So that's what I'm saying. So this is basically this. So from here you can get this. This is the same as this. So that's
No,
what I'm asking you to prove. So you will assume
no,
the
sir. The
first
first
equations.
equality.
Sorry.
The first equality after you wrote IQU.
This one to this one, no?
No, sir.
Oh,
How are you
this.
writing the U?
Huh.
The U, how are you writing it as this time average of EX EY star plus
So
EY
that
EX
that is the definition. See, that is what I'm saying. So I am asking you to prove the equivalence of these two. Okay, so if you actually start with the equations of the field that we used in the Jones treatment, where delta is actually del x minus del y. Okay, if you start from that, you can straight prove that this is going to be this. Okay, that's what I'm asking you to prove. I can prove it to you, but it's okay. I mean, you can easily do it actually. It's a very simple thing. I actually, yeah, I mean, it is not difficult at all. It's very simple proof. Okay, so you just start from, just write your ex as e0x cos of omega t plus delta x, and e0y as, I mean, sorry, as ey as e0y cos of omega t plus delta y, and then you try to basically eliminate omega t. Okay, then you will basically just exactly get this. So I will, you can do it very easily. Okay,
Sir,
so
I think
you,
he's asking why we have defined IQU in that way, the time average of EXX.
The IQ and V are like IQ is fine. The only
hmm.
problem I have is with the U and V. But that is fine. Like we can maybe prove
Yeah,
this
you
thing
can.
and
So basically, no, are you asking that why measuring all this will give you the representation of all states? Because
no,
that
sir.
is a different question from saying
No,
why this is
I,
equal to this.
no.
If you're
I'm not
asking,
going to the third equality.
so you're saying
I'm
why
just
that is equal to this.
yes. Why U is equals to that and V is equals to this.
So that best see. Okay, so the starting point was actually Stokes did not do it this way. Okay, Stokes did it by this way. Okay, he did it as this, and from there you can get this. From here you can get this. Okay, so that is
Oh,
what I am sort of asking you to look at. And
okay.
there are some simple hints I can tell you, in the sense that you can, okay, let me just make this shorter. uh, so basically, if you just start with ex of t equals e0x cos of omega t plus delta x, and eyt as e0y cos of uh, omega t plus delta y. Okay, and then you sort of you try to eliminate omega t. Okay,
Sir,
okay.
won't
uh,
e to the power I omega t, that
yeah,
would, I
that
think,
also you
we
can do.
deal with.
Absolutely. Whatever. See, I had done it last time with this thing. I mean, exactly. I mean, you can basically take, ex e to the e0x e to the I phi, and ey you can take as e0y e to the I phi, and some plus minus some delta. So that delta is, so typically when I say that, so I start with this one, right? So then I will essentially say that your ex is e0x e to the I phi, and your ey is e0y e to the I phi plus minus pi by 4, because this is what I've taken. So if I do that, you will basically get all this. That also is possible. So I did not see these are. I think you guys can easily do this. I don't need to tell you. Very simply, you can do. Just from here, if you start with this, you will easily get u as this. Keeping in mind that these are the definitions. Okay, so if you take horizontal vertical or horizontal minus vertical, this minus 45, and this minus RCP minus LCP, you can easily get. It's not a problem at all. Okay, so you just prove it like that. Okay, so
Sir, I have a question.
huh,
So here in this formalism, we are writing matrices 4 cross 4, right? We are using four
four
angles,
cross one
0.
at the moment. Four cross
So
one, yeah.
at the moment, but then eventually
Hmm.
we'll define a 4 cross 4
No,
matrix,
here I'm defining. So Rohan, this is where I'm defining
right?
this one.
So we are using the angles 0, 45, and 135 and
Yes, yes.
90, right?
Hmm,
Uh,
hmm.
so we are using 4 angles. But I think we can define the whole formalism in just 3 angles, which is 0, 60, and 120. But I think in that we will lose the information of the circular
RCP
correlation.
LCP. Yes, correct.
Yeah, like
RCP
that.
LCP will lose.
that was, I think, one. I think it's the same doubt as it is. Like, basically, in all the four, we are taking the different bases to find out
Yes,
the intensity to cover
yes,
everything.
yes,
So
correct.
I can understand horizontal and vertical because that's like one of the most common bases we take, and then you take the minus.
Mm.
Like, how did the, like, intuitively, how can you tell that h minus b and p plus m both also need to be taken for LCP RCP? I understand it's a different basis which is not there in any linear one.
Right,
H
right.
plus b I can understand,
Mm.
but for h minus b and
So,
p plus m, is there any
no,
intuitive way
H
to do
minus
that?
V. So no. Oh, you're saying H minus V and P plus M.
Yeah, like those two,
But
like how can you
so
intuitively say
see,
that?
basically, Priyanuj, this is H minus. See, so these are the states of different linear polarization. Okay, in the sense that I am finding out. Uh, uh, so if you think of 45 and so if see P plus M, say it's better P minus minus P, 45 minus minus 45. Okay, so
Hmm.
it is like you can span the entire angle between, so this is like 90, 0 and 90. Okay, and this is like 45 and minus 45. So the whole sphere, so it's, if you just think of like, all sine tan cos that way, so between 0 and 180, if you can find out, then the rest of the things are also covered.
Hmm.
In a sense, if you
One
covered that thing, then the other ones also will get covered, right? So basically so this is the degree of linear polarization, na? When a q plus u divide this thing. So so essentially you are, remember that these are the three things that you are really bothered about. These things. So these things tell you whatever information that is there. Okay. So I mean, see, 45 and minus 45, in the sense that I can just, if I want to, go to, you see, other higher ones. It is like I can represent any other angle by a ratio of this and this. This is the total intensity. Okay, this is my normalization factor line. This one basically I just, so if it is perfectly polarized, then all these will be one, and then this is just, it will be a 1 1 0 0 and all that kind of thing, right? But I can, the whole point is that I can write the other polarizations in terms of some coefficients along with these actually. Okay, now whether you can write other, I mean, if you can take other bases, see, the whole thing is again the 45, as Rohan said, I mean, 90 and 45, I mean, when I do LCP minus RCP, that also is basically the phase angle between them is still 90, right? So if I just take 45, see, this rendition is beautiful, right? Just cos delta and sine delta, with delta being this, actually give you both linear and circular. I think this is quite nice, right? This thing you will not get by choice of any other angle of delta, right?
Okay, I
Just the
guess,
cos
like,
component
that
gives
way.
you linear and
Hmm.
the sine component gives you circular. That is quite novel, right? That
Hmm.
is quite unique, I would say.
Yeah, I think, like, we can only
I
find
think
about
that is the
like
main thing.
information
That is, I
about the
would say,
phase only if we take P and M and RL as
yes,
combination.
yes,
That's what you're
yes,
saying, right?
yes,
With the
yes, yes.
first two, I can't find any information about the phase.
No,
Yeah,
nothing. It's only the, so I will just, let me just paste the other, all the things. Acha, do I have to get out of this? I think I have to. Oh God, just paste all that. Okay, so these are basically the things. Okay, so these are perfectly, yeah. So this is the most general thing. This is the most general thing. Okay, where it's elliptical, and as you see, you can, you know what alpha and epsilon are. This is that azimuth, and this is that this thing, your electricity angle. Okay, so basically a combination, I think why you choose 45 is essentially because of this. I mean, you can write these two and then represent both, circular and linear as a function of this. And I think, see, I think basically this is what, see, remember, if I want to measure, just I will essentially these measurements, this DOCP, DOLP and DOCP, These give me all my information. Okay, so root of this q square plus u square by, I remember, see, so what is mattering is only the second and the third term. Okay, the first term obviously is a normalization factor, right? So from here, whatever it is, if it's not 45 or something, even that, I can actually get whatever the angle is from here, from these. But of course, as I said, by choosing other angles, it is in principle the coefficients will just, so it's just basically you are shifting your baseline somewhat, right? But the circular one you will never be able to represent by a single this thing, by a single choice of angle. You will not be able to represent the circular polarization all in using a single formalism if you don't choose 45. I think that is why it was chosen like that. Okay, so this A, by the way, is the important factor. So that if you just if I unravel this, make this is the main equation, and if I now want to represent this from here, this A will essentially be something like 1 0 0 1 1 0 0 minus 1 0 1 1 0, and acha, this one you please check. Okay, I think this is something like this. You can please check this. Okay, this one please check. I this last two maybe I might have written wrong.
Sir, is there any significance of the first one? It's one in all of the states, right? Like
Sorry, one in what?
IH plus IV.
That is total intensity, no?
Yeah.
That is the total intensity.
Oh, so that can be used to calibrate or something.
Exactly. That is the calibration factor. See, what is nice, so how basically you are, so see, remember what we wrote as the determinant of the phi, na? So you see the determinant of phi can be written exactly in terms of these. So if you remember the definition we wrote, 1 minus, I think it was 4, what was that? I forgot. Something like, so degree of polarization, right? So degree of polarization we wrote was root of 1 minus 4 determined phi by trace phi whole square or something. So you can see that this determinant of phi is actually directly relatable to this. So I wrote this wrong. This is just given by 1/4 of I square minus q square plus u square plus v square. And see, so this you can check. So determinant of phi, remember, was just ex star ay star minus that. So you try that out, you will see this will succeed, and they beautifully come in actually. So just like we saw that for perfectly polarized state, then your determinant of phi has to be 0, right? And that is basically, that means the degree of polarization has to be 1, right? Which means this is 1, mane I is equal to this, so determinant of phi is 0.
Sir,
Okay.
I think in that A, that iota and minus iota are reversed.
Are they reversed?
I mean,
अच्छा
it should be
please check.
first minus I and then I.
ये check करो यार. तुम please check this and tell me.
Yeah, sir. Yeah, I think it would be
Huh?
minus I because
Minus
5yx is the third term.
Okay, I don't know. I wrote somewhere. Okay, maybe it's wrong. Okay. Okay, I'm then putting this. I'm just putting this. So, acha, please check. I'll change it once everybody confirms. Is everybody confirming? Abhi, I don't want to waste time. Okay, you just check on WhatsApp and tell me if this is wrong. Okay, then I'll change in the notes. Okay, at the moment, two of you are saying, but I will have to calculate this myself and check. Abhi, I
Sir,
don't know.
minus I
Minus I.
only.
Acha,
Yeah,
theek hai.
minus
Yes,
I.
correct. So since that is coming from everybody, let me just check. Okay, minus I. Okay. So what is very interesting is that, see, I mean, this is, so just as we know that the phi has to be so non-negative, phi, we saw that from the last this thing, that the phi basically has to be so we wrote down the conditions for some any 2 by 2 matrix being a density, I mean, sorry, not density matrix, being the coherency. By the way, that density matrix and coherency matrix are same actually. Okay, exactly same. I mean, what you have in quantum mechanics, that thing that we call density matrix, that is not different from this. Okay, that is exactly. So there again, I'm digressing a bit, but I think it is interesting because coherency matrix, what you have as the diagonal things, those are the pure states. I mean, when you have a pure state density matrix, then the off diagonal terms are zero. But for mixed states, you have those non-zero, right? And those are the measure of the coherences. Or if you have non-zero density matrix, you are basically having some kind of decoherence coming in. Okay, so just here of course it's slightly different from there, because here it is not well, so it is not that there is, so the off diagonal terms are not really measuring coherence, I mean non-coherence or something like that. But it is a fact that when you have perfectly coherent state, I mean sorry, perfectly polarized states, then the determinant is zero. Okay, it is only when those off diagonals are different from these things, then you have degree of polarization. I mean, not, I mean, you don't have perfectly polarized states. Okay, just like the, so I think I think it will be useful for us to have a discussion on density matrix in quantum mechanics and coherency matrix in light. I think it's going to be quite nice. So I would again offer this on maybe Friday or something. If some, I won't do it. I think you guys should come ahead and do it. Okay, so basically just as yeah, so basically this non-negativity of phi implies your degree of polarization less equal 1. So this same way, so this basically implies that the determinant of phi is essentially given by this I total square minus I polarized component square. So this basically what I want to mean here is that uh, so so the determinant of phi, that is something like the measure of the unpolarized component of the partially polarized light. Okay, so I total square mane it's the sort of total intensity light, and the I polarization is the polarized component of that. So remember, when your I total is equal to I polarization, then your determinant is zero. Okay, so what is crucial is that if you have a non-zero determinant of the coherency matrix, that means that the light is partially polarized. Okay, that is very important for us to note that, and remember that the non-zero component essentially will come when the off diagonal terms are unequal. So there is so I it is, to in spirit, it is kind of saying that there are these there is a so you can always say that lack of polarization is also somewhat related to lack of perfect coherency or something. When you have perfectly coherent light, you will always have this coherency matrix to be zero, and if there is any decoherence coming in, then you will actually, so that way one can actually say that perfectly polarized light is actually impossible, because only when you have perfectly coherent states, I should not say, I mean in the sense that light which has infinite coherence, or basically the line width, as we say, is completely zero. Okay, only then you can have absolutely perfect polarization. These are somewhat mixed, but there is no well, in the sense whether when one can actually draw a direct analogy from coherence time to this, that I think is not so. I don't know whether this is being done. Okay, so what I'm claiming is, if you have uh, finite coherence time and finite coherence, you will also have a finite polarization. in the sense that the degree of polarization will not be 1. Okay, this is quite nice. So now we will just, one important part that we need to do is the Poincare sphere. So that I will again, I think most of you know it, but let me just still write it down. So basically the so so the Stokes vectors are essentially represented in this kind of a notation where this Poincare sphere. Let me again, I have taken it from here. Right. So this is a sphere where so these are the geometrical representation of the Stokes vectors essentially. So I think most of you are aware of this, that the poles and the on the equator, they represent different polarization states. So this is like north pole is the left LCP, this is the RCP. Equator represents different linear polarization states. Okay, and what is interesting is any totally polarized light will fall on the surface of the sphere. Anything that is within the sphere is essentially partially polarized. Okay, totally polarized states, that is very crucial. And so it is typically what we write down is that this is a geometrical representation of all possible polarization states. Yeah. And you also have, when we construct this, we have the normalized Stokes vectors, which are given by some S. Oh, so I write the transversely, I'm writing. So instead of column, I'm writing them as a row. So it is basically I q by, so I just divide by the normalized, the normal, the total intensity. Okay, this is typically how you construct. Okay, so after this, of course, these are typically written as small a. Okay, so one small u, one u, one u. Okay. So from here, so Priyanuj will just tell us, I'll finish in 5 minutes. So Priyanuj will tell us in the next 10 minutes what he had done in this thing. So what is now, we go to description of representation of partially polarizing optical elements. And that is the Muller matrix, which was developed by Herr Muller sometime in the 40s again. And that essentially means that, so you want to find out how light, which is partially polarized and which has a Stokes vector, input Stokes vector, how an optical element will transform that input Stokes vector into another Stokes vector, right? So basically you have a S output given by an M S input. Okay, so that essentially means that I have some IO, QO, UO, VO given by an M11, M12 करके M14, M21 or M31, M41, all these things to M44 II, QI, UI, and VI. Okay, so this is my Muller matrix, and any kind of optical element completely can be described. Completely can be described. Okay, and there are of course some interesting things that, or things that we typically know. There are retarders, the half wave plate, quarter wave plate. All these have different Muller matrix, and now what one can basically, that is very important for you to note, is that the coherency matrix formalism, okay, allows us to establish a relationship between the Jones and the Muller-Stokes formalism. That is very important. So once the Jones formalism is easy to find out, it's a 2 cross 2 matrix. But if you know the Jones vector of any optical element, then you can use actually something just we did right now to get the Muller matrix of that of that object. Okay, and that is given by a simple. So basically, let me just yeah. So the using the phi matrix formalism allows one to establish a relationship between the Jones and Stokes-Muller formalisms. So again, this is something that I'm writing down, but this also can be proved. So this is that A matrix that we wrote down, right? So any Muller matrix can be obtained from a Jones matrix by a tensorial. This is very crucial. Tensorial, tensor product between the Jones and this is the J star of that. You can basically find out any Muller matrix from whatever Jones matrix you have. Okay, so if you take a polarizer, if you take a retarder, anything, you can just construct this Muller matrix by using this. This is a very important relationship. Okay, so typically, however, in experiments, what people do is that one measures, it is easier to sort of measure this. I mean, for example, so the power of the Muller matrix is, see, the optical elements are very simple. That is not what really is so great. But suppose I'm trying to find out, say, we are doing some kind of tissue, so tissues, cells, tissues, they're biological tissues. They are highly depolarizing, okay? And this is a fantastic way of actually, from the polarization transfer that happens because of interaction of light with the tissue, actually allows you to find out some very interesting properties of the tissue. For example, it's used very much in diagnostics. So you have healthy tissues, so they have depolarizing properties. And if you know the Muller matrix of a healthy tissue, and then if you take a diseased tissue and find the Muller matrix of the diseased tissue, and find there's a difference within, like, which are more than experimental errors, then you can actually say that there is a problem in the tissue. Okay, so what people typically do is you actually measure the output Stokes vectors and the input Stokes vector. So this is easy for the input light, that, and this also is, you can do, you can measure the output light also by the series of, by just wave plate and polarizer, you can measure, and from then you basically you have this kind of relationship, and you can actually, there are many things. So if you read the chapter 6 of the textbook, of our textbook, it actually tells you of this eigenvalue calibration method. So that is a detail, so I have not really gone into that, but that's a very good way of actually calculating the Muller matrices. Okay, but even from here you can sort of calculate, if you know this and that, it is possible to find out the Muller matrix of any optical element, of any sort of some kind of a element which has polarizing properties. Okay, so this is the main equation that you have. And another thing that is important is, if you want, so any kind of rotation, that is. So just as we saw that if you take an optical element and rotate it, then the Jones vector is rotated by the typical the rotation matrix in 2D. For if you so for this for here, it will be the rotation matrix that you have in the 4x4 space, right? So basically for rotated optical elements, you will have some m dashed equal to the this is not that, this is the inverse, the t minus 1 alpha m t alpha, where basically the t alpha is given by, so the 4x4 thing, 1 0 0 0 0 cos 2 alpha sine 2 alpha 0 0 0 minus sine 2 alpha cos 2 alpha 0 0 0 0 1. So this you can actually find out from by here, by this also, from that thing that we had for Jones. Okay, you can verify this. This is the 4x4. So anything that you have for a certain optical element, if you rotate it by a certain angle, then this is the transformation matrix that you should use. Okay, so I will ask you to calculate some Muller matrices for certain optical elements, and I think that will be useful. And I really ask you to study chapter 6. Okay, so tell me now. We will any questions? So I don't want to go into too much of details in this thing, because there are some other things also. So properties like die attenuation and retardance. So retardance is essentially what you have in the for a quarter wave plate. So die attenuation is an interesting thing. So that is essentially so if you have any optical element which has different properties for vertical and horizontal input polarization, then that is a measure of die attenuation. So how it reacts for horizontal and how it reacts for vertical is different. So there are these certain properties that we use to characterize different elements. So those are again information. So you can just read the textbook and you can figure out those, get those bits of information. But the basic concepts are, however, I think these. Okay. So tell me, what is the status? Can we have Priyanu just briefly explain what he had done in the experiment?
Yeah,
Or do you have
sir.
any
I
questions?
actually have a presentation. I made one.
So, by the way, so guys, is this fine? I mean, do you have any other queries? These things I will stop presenting then and hand over to Priyanu if everybody is fine, because this is an important area. But then, I think it is well covered in the textbook, and I think I think we have discussed most of the important concepts. So, can Priyanu start then? Okay, and let me stop presenting. So Priyanuj, I think please take over. Yeah, so make it full screen, huh? Beautiful. Yeah, like nice. Priyanuj, we cannot hear you. Hey, you are mute, yeah. What? Unmute yourself.
Sorry,
Ah,
I didn't
you
realize I
stop. See, you understand what is the problem of doing online teaching, no?
was. Yes. So yeah,
Ah,
so I made a brief presentation about one particular experiment in our advanced optics lab, where we observed the physical realization of geometric phase of light, especially particularly which is the Pancharatnam Berry phase. So first, till now, all the in the experiments, the phase that we have occurred are something called dynamical phase, as in the phase that the wave gets is through actually passing through the passing through what you call optical elements, and the phase incurred is directly proportional to the optical path length that they covered, and hence the name, it's named dynamical phase. But there's also one other type of phase that can be induced on light, which does not depend on the path length. Rather, it depends on the topology of the evolution of the wave itself. Hence, it's called the geometric phase. In geometric phase, so basically, to have a phase in to have a phase difference in your two electric fields, you need to bring about some sort of difference between the two in terms of, I guess, in phase. So another way of doing it is to change the polarization state of the electromagnetic wave when it undergoes evolution in a inhomogeneous isotropic or an isotropic medium. This is one of the key parts. We need this for to attain geometric phase. So I'll be just giving a very short introduction what the two types of geometric phase are. One is spin Berry redirection and one is Pancharatham Berry. Focus will be more on Pancharatham Berry phase. In speed redirection Berry phase, the wave propagates in such a way that the k vector for the wave itself changes adiabatically, or in simple language, it moves so smoothly that in the local frame the polarization axis or the polarization state of the wave itself does not change. However, after, if you look at the global frame, the polarization state does actually change, which is shown in figure A. As you can see, if when it starts from here, due to this path taken, due to the adiabatic change of the k vector, finally when you reach here, you in the local frame you won't realize any change, but in the global frame you will see that there is an optical rotation of the in this case the linear polarization vector. Why does this happen? It happens because upon the adiabatic change, you if you do a full rotation in k space, the angle that is subtended by this full rotation is manifested as a change in the polarization state. And why is this a geometric phase? Because irrespective of the path taken, as long as you make a circle in the k space, you will have the same phase. So it does not depend on the path. You just have to make sure it traverses the same circle on the k sphere. So this is just been a redirection phase, which is not our main focus. This one is of our focus, which is the Pancharatnam Berry phase.
So
In this,
one just a thing is that this you find when you pass light through a twisted optical fiber. So
yes,
if you're going through a twisted optical fiber, then you are sort of doing this thing.
And not circular. Any
sorry,
closed
Any closed path, yeah, you don't need not be circular. That is true,
okay,
absolutely true. Any closed path, that is important. So basically, guys, I understand this very simply. So as Priyanuj said, that you basically have the path change, dynamic. So there are two ways you can get phase shift. One is by dynamic phase. That is very simple. So you just consider if you have ex. So say some e of z as some e0 z e to the I k dot z minus omega t. So that kz minus omega t is the phi, right? So if you change z, then obviously phi changes. Now, however, if you do not change z, but k you take as a vector and k you sort of go through a closed path, that changes, right? So k is changes, then still you get a change in path, phase, right? Or if you have go to E0, that is the direction of the electric field, right? So that also, if you write as E0 e to the I phi, something, and you change the direction of E0, that means that total phi is actually changing. So geometrical phase is essentially changing all other parameters except the path, which is the z. I think that is a very easy way
yes,
that
yes,
I feel to understand geometric phase.
yes.
Okay, continue, Priyanuj.
Yeah, so as Sir said, the change, there's also another way of doing it by changing the E. That is basically what we do in Pachanandam Berry phase, where the K does not change and X, it does not change in the geometric phase, but we somehow continuously change the E naught, which is that we change the electric field vector or basically the polarization. And in this phase, if you can somehow do a full cyclic evolution in the polarization state phase, which will be visually shown next, you can actually incur a phase without any change in the path length. And yeah, so that leads to an additional geometric phase factor. And one best way to see is using the Poincare sphere. The Poincare sphere, I think Sir has already explained, but any general point of the Poincare sphere is represented by these three coordinates, which is q by I, u by I, and v by I. The radius of the Poincare sphere is the degree of polarization. So basically, all light that is on the surface of the Poincare sphere is completely polarized, and anything with a lesser radius is partially polarized. And now I'll show how you can incur a phase because of a full cyclic evolution in the Poincare sphere. Suppose we take a linearly polarized light that starts at A through some optical element. If we can make it a right circular polarized light, so a circularly polarized light is represented on the top of the Poincare sphere, and left circularly polarized light is on the bottom. So basically, poles represent circularly polarized light, and the equatorial plane is your linearly polarized light. So first, after an optical element, the linearly polarized light will be made into a circularly polarized light. Then again, after passing to another optical element, we have to make it again linearly polarized. However, but not at the same angle. It has to be different. The orientation of the polarization vector. Then again, you pass through another element, which will make it left circularly polarized light, and then finally, by a similar optical element, you traverse a full circle in the polarization space, and it can be shown that the phase added to this wave that has transversed from A, B, C, D, A, the phase added is actually half of the solid angle of ABDCA. So let us look at a experimental way of observing this. So this was the experiment we did. So which was the interferometric realization of PV phase. I will show you part by part which part causes what movement on the Poincare sphere. First, suppose you have light coming out of the laser, and there are two paths. One path has no optical element, and one path has two quarter wave plates, where the first one is oriented such a way that the light coming from the laser, the linearly polarized light, will be turned into a circularly polarized light. The second quarter wave plate is rotated at pi by 2 plus beta. The angle will make sense when I'll tell you the results, but it's oriented in such a way for a very particular reason. So first, when light passes through the polarizer, we will be on the point A on the Poincare sphere. Then when the light passes through the beam splitter and through the first quarter wave plate, the linearly polarized light will become circularly polarized light. And because the second quarter wave plate is oriented pi by 2 plus beta, it will make the circularly polarized light linearly polarized, but the orientation will be different. That is why the pi by 2 plus beta factor is very important.
So this
It will
is
make
exactly, guys, what I told you that day, right? That alpha plus epsilon that I asked you to measure. No, if you have a certain eccentricity angle, how do you measure? This is exactly what you are doing. You
Yes.
understand? You are basically putting that at a different angle, and then the linearly polarized light basically has that angle added to it.
Yeah.
Exactly that. So just yeah, this is what I told you that day.
And then once it hits the mirror, it reflects back. The polarization still remains the same. But passing through the second quarter wave plate again from the other side, the linearly polarized light will become circular, but in the opposite direction. So it will be now LCP. Then again passing through the first quarter wave plate, it comes back to the initial polarization state, which was at A. So for both the path from path for the mirror M1, there is no phase added, or like with respect to P2, because there is no optical element. But in the second one, there is a phase added from what I mentioned before. The phase added will be half angle of it will be half of the solid angle of the path that is traversed on the Poincare sphere, and here it is twice beta. And why is it twice into beta? Because that's the fact that light passes through the second quarter wave plate twice, and that's why each time it passes through, actually e to the power of I beta gets added to the wave. So because it passes twice, you get a e to the power minus twice I beta. So twice beta, so that's why you have a twice beta added phase with respect to the wave that's coming from, light that's coming from mirror one. And so that itself will give you some path difference that will manifest itself as a phase difference between P1. So when you interfere both waves, you will get some fringes. And changing B, as in rotating your second quarter wave plate, you can actually, by changing the beta, you change the phase difference between the two. Hence, your fringes will also shift. So this is like a very easy way to see how just changing the geometricity of your equipment, no, there is no change in optical path length. You are actually shifting the fringes. You're changing the phase without any change in optical path length. Yes, sir. Like this
Yeah,
is
very
explained.
nice, very nice. So, any comments, questions? I mean, it's a pity that many of you guys missed it. So, I have been keeping on saying that, this is a course where people who are interested in optics should just do all the experiments. But yeah, I mean, it's really a pity. So, I hope, you guys, there will be some normalcy at least next summer or whenever, and you guys should come and just do this experiment. And I will cooperate with you fully. I mean, whenever you want, I will. Whoever is interested, I will absolutely, ensure that you can do this experiment. This experiment, the fiber optics, the SLM, these three you should certainly do. Any comments, questions?
Sir, the fringes that we get are if there is a dynamical phase, then there won't be any fringes, right?
Yeah, if there is dynamic phase, I mean fringe. That if there is dynamic phase, obviously that's an additional thing, but you get this over and above that actually.
Right, but I'm asking, what is the difference between a dynamic phase and a geometric phase? Like, because of the
Now,
dynamic phase, we don't see fringes, but
yeah,
here
yeah,
we
dynamic.
have.
See, the effect finally is fringes for both, na. But here you will see that just by rotating this thing, you can actually change the fringe contrast tremendously, and you can also change the fringes move. So by rotating this cube, this quarter wave plate too, you can actually see the fringes move, and you can, in principle, if there are like this is of course by two quarter wave plate, man, you will always get some kind of linear polarized light. So they will, but then remember, you are absolutely not changing the the mirrors in any way. So, for example, if you remove the quarter wave plates again, if there is any path, I mean, you will of course get some kind of fringes, some fixed fringes, but the you will see that because of these two, this thing, some effect of quarter wave plate two will be very much there when you will see the some kind of fringes that will rotate, that will shift as you change this. So the way they do the measurement is that they see one full fringe shift.
Okay, so the difference is if we change the path lengths, the contrast will change. But if we
Yes, yes, yes.
change the angle between that quarter wave plate 1 and 2, the fringes actually just shift. There is no
Shift,
contrast.
yes, correct. You will see them shifting, right, Priyanus? That's what you saw, no?
Yeah, yeah. Oh no, the angle of the, like, we change the angle of the quarter wave plate, which is like we change the angle of the optic axis, not
Yes,
actually
yes,
like
yes.
the literal quarter wave plate by
No,
making
no, no. Of course, of
that would
course.
change
Yeah,
the
yeah, yeah.
optical path. That way of
Right,
changing
right.
will also, yeah, but
So
yeah, I think
optical path is undisturbed. You
yeah,
absolutely don't change the
undisturbed,
optical
no
path.
change.
No change. It's just that the optic axis you rotate so that it traverses a sort of a some path in the Poincare sphere. Okay, so that is the beauty of this. So that is really, I mean, you guys should just, if you're interested, to do this experiment,
But
and you
sir,
can do
here,
it. I mean,
sir, we can
given.
think about it about like is that see in the Michelson in the second year, what we do is that we actually rotate the glass and we see the fringe actually move, right? So there we are actually changing the dynamic phase, and here we are
Yes,
just
yes,
rotating the quarter. So here
absolutely.
we're changing the fringes move.
Absolutely, absolutely. So remember in the Michelson, in the second year experiment, there is a glass plate put in one of the paths. So instead of water wave plate, you put that just a microscope slide, na, and then you rotate that slide and you see that the fringes shift, and you find out how much you rotate and then how many fringes shift, and from that angle you can get the refractive index of the glass, right? So here you don't change anything; you just change you absolutely don't touch the path length. But acha, one thing, Priyanuj, when you are doing the experiment, the dynamic phase ke liye you get some fringes also, na?
No,
So there will be
actually,
some.
fringes
Huh?
itself is because of, I think, dynamical phase, because you get like a, you technically,
Yeah, 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 yeah.
yeah,
Obviously, what a stupid
yeah.
fool. Yeah, yeah. Of course, of course. Yeah. So
But the
Rohan, you
shift
will
in the
always
fringes,
get fringes. Exactly. Yeah, whatever. Yeah,
Yeah,
very
I
stupidly
got
I
it.
said. So you will always get fringes, but they will move when you change the quarter wave plate. Absolutely.
Sir, but what is the difference between rotating the quarter wave plate and shifting the fringes and rotating a glass plate and shifting the
No,
fringes?
but yeah, yeah, exactly. So when you rotate the glass plate, you're actually changing the refractive index, right? So, you're changing the optical
Path
path
length.
through the glass, right?
Yeah.
So if you change the optical path through the glass, that means the delta x is changing. So think of that k dot z, right? So that k z is changing. So because of that, phi is changing. Here, you're not doing that. Here you have the E0. So E0 has a e to the I phi or something. That one is changing, right? So the E0 का direction, E0 का जो phi angle है उसका, that is changing. So that is giving you a change in the total actual phase there. So when these two interfere, when the two perpendicular beams interfere, that is manifested as a fringe shift. So when you are rotating the glass slide, you are changing the delta Z. But when you are changing the quarter wave plate, you are actually changing the E के साथ जो phi है, माने E0 के साथ जो phi है.
Oh, okay.
You understand? If you want, I can
Yes.
just write it down. Wait, maybe people are not, maybe it's not clear.
Yeah,
Let
I
me
think the
just.
confusion is that we rotated the glass. If suppose Z axis, we are not rotating about the same axis. Rotating to,
No, yeah. So
yeah, I
I
think
think Priyanuj, you just stop sharing. I will write some equation so they will understand.
like
So
if you
just
can say I
let
think
me.
draw it, it will be easier
Yeah,
to
yeah, yeah.
understand.
I'll not draw nahi. I'll just write that. So basically, where is it? Stop presenting.
Oh wait, I have to
Where is
stop
it?
sharing.
Where is it? So basically, so this is completely out of context, however, but still. So essentially, if you just, I'm writing this separate thing completely. Okay. So you have your, typically you have your E of say zt as E0 vector e to the I k dot z minus omega t, right? So this is your phi, right? So phi can change when you change to z plus delta z, or also if you change this k, that basically is your spin redirection. And your E0 that I can write as some E0, this thing as e to the I phi. This is basically your Pancharatnam. This is when you are traversing the Poincare sphere. You understand? When this is pi by 4 or whatever, then this is basically linear. This is pi by 2, one it's circular. Right? So this is the thing that, but then this is included in this all whole phase factor, right? And I can actually include this one here. So when I'm changing either this or this k, I'm actually finally changing this whole thing. So when I change just z,
So
that is dynamical phase.
I didn't understand how this is manifested. Like how do you show that in Pancharatnam we are changing this phi? Like
No, basically what I'm trying to say is, see, when I'm going from linear, then this is pi by 4 or 0, right? When I'm actually in, say, when I'm at circular or elliptical, then I have some intermediate, e to the I pi by 2 basically means I am circular, right? When I'm going
sir,
from pi by 2 to say
circular.
pi by 4, I'm getting some phase, na?
Uh,
That is what I'm trying to say. So basically when I'm here, say, let me try to make this bigger if possible. Oh shit. Oh, this whole thing is grouped, is it? Oh man, I can't select this.
Yeah,
Anyway,
actually, I
you
think
can see.
uh,
So
I think
basically,
Aniruddha's question is that right, it's very physically hard to imagine how like geometric phase is happening. Like we can understand like the end result and how it is happening through the maths or the
yeah.
point crest.
So exactly. So I am trying to sort of simplify this by saying that when I'm at pi by 4 or 0, I'm basically somewhere here. But when I'm at the LCP, RCP, pi by 2 minus pi by 2 here, plus pi by 2 here, right? And elliptical means any of these somewhere like that. Right, so that is what I'm saying. So just to simplify this, I'm saying that if I write this one as something like this, where this phi is an angle on the Poincare sphere. Okay, so basically that kind of thing, that is when I change this, I'm actually moving around the Poincare sphere, so I'm changing the direction of the polarization, and that gets, however, included in this phase element. So when you are actually interfering with another path, you get a phase difference. Okay, so it does not matter whether it's a change in this one or change in this one. There is still a change in the phase. When you actually interfere, you get actual effects in the fringe.
sir, I just didn't understand like physically where did the geometric thing come from? Like where did the phase come from? Like I know that changing that phi will result in a drift in phase.
So basically, it's the area in the curve. That area that you are traversing in this, that area basically causes, that area closed, that area enclosed in that path. That is a something like some work done. Okay, that work done basically. I mean, yeah, it's an audacious statement I'm making, but it's
Yeah,
close to that. That area enclosed. That
so
is typically a
whatever you're
measurement
saying,
of
I
the
don't, I'm not getting
geometric
the
phase.
feel of it. Like, how do you show this?
Aha. Okay. How do you show that
No,
area
sir.
is?
Yeah,
But
here you can show actually. If you see,
uh,
you write the Jones matrix. Let's say you
uh,
know
uh,
that what will be the Jones matrix of a quadruplet. Okay, it's easy. So you put a like let's say you start with a x polarized light. You put a quadruplet and you write that what will be the Jones matrix of a quadruplet rotating with beta angle.
basically,
And
ये है ना given this one only will change.
yeah,
इसको
exactly.
तुम
So
exactly वही तो change होगा, right?
yeah, yeah. So you can see that there will be an extra e to the power I beta term when you
Yeah.
e out. Actually, you
वही
can
तो मैं
see this.
बोला यार.
Yeah.
Exactly वही तो मैं बोला. That beta term
Yeah.
will add on here.
Every time we pass to the second quarter wave plate, the entire thing gets multiplied by e to the power y beta. But there's a like why does but that is what is happening after every time it passes the second quarter wave plate.
So basically, as you, Anirudh, if I write this as this is basically like the Jones vector itself, na? So typically, if it's e x y or something, well, it's same. Mane, I am saying simply as one just a number, but in principle, this is a Jones vector, no? So when you do a Jones vector, when you are rotating the quadratic money, you are basically changing the Jones vector. Means you will just get a phase term outside. But exactly this, nothing but this. What I wrote here, exactly this. So do you? Yeah. So now, if you tell why that an area enclosed is the total phase, that again I would say that you do by the Jones treatment or Stokes treatment, you will get that.
I didn't understand how did we get an area over there? Like, can you just take me through the path again? Like,
That I need to hand over back to Priyanuj. He has the thing. Wait.
And sir, already we have a talk na, about these things in the that term paper.
That is there. That is that. I think I don't know where that is your guy. Up to you. Yeah, I mean, yeah, there is a. I think. But did somebody take that Muller matrix thing?
Yes, yes. No, not Muller matrix. This
Oh, that
geometrical
geometrical
phase.
phase somebody took, na?
Yes, yes, yes.
Anyway,
You would
so
have taken.
once Priyanuj, if people have time or whatever, as Anirudh asked, you can just show the path once more. You can just start
Okay.
presenting it. Yeah.
Wait a second.
also, Priyanuj, unmute yourself.
Yeah, yeah, yeah.
Mute yourself, please.
I think
No, now you are
no.
not showing. We cannot see anything.
The problem is my thing is on, but it can't. Okay, wait.
No, you need
Now,
to become two Priyanujas. Last
presenting.
time you had
So,
another one more came in, then it worked.
okay.
I don't know
So
why
Now you can see,
you
right?
guys face a problem here.
Now,
आई तो आ
now
गया आ गया आ गया
wait.
आ गया
I'll show. Wait. I'll show for the big one.
this
Here.
one this
Okay. So, Aniruddha, you have to tell which part. Like,
so that is the
just,
whole area that
just take me
BADCB
just take me through how the laser just take
oh,
me
okay.
through the path of the laser on
Yeah.
this.
part
So,
of the हाँ oh वो तो
okay.
ठीक है
Fine. So when you go past the first polarizer, it will be at A. So that's fine. That a linearly polarized light, you take any arbitrary one. So it's A. After the first quarter wave plate, it will become RCB. So it's B. After the second quarter wave plate, because it's at a different angle, it's linearly polarized, but it's having a different orientation. And every orientation has a place in on the equator. So if it's going to be different, it can't be A. So it'll be somewhere else.
Okay, I got it. This was the problem. I
Yeah.
was thinking why
Yeah, like that's the
they
main
don't
thing.
coincide.
You have to, that's a quarter wave plate two's orientation is the most crucial part. It
Yeah,
and
yeah.
that's why in some parts you will have no phase added when both of them are I think perfectly pi by two.
So basically, there can be instances where A and
Yeah,
C
yeah.
coincide. There can be instances
No,
where
no
C is
phase.
on the exact opposite end of A also.
Yeah,
It
that.
depends on the orientation of the relative
Yeah, yeah.
orientation
So
of QP1
as
and
I
QP2.
rotate quarter wave plate two, my C can transverse entire
circumference.
equator, huh? Yeah, circumference, correct.
Okay, I think I got it. Yeah. So basically, then you're saying that the solid angle. Acha, one more doubt I had. Like, how did you say solid, like equate solid angle and angle? Like,
Oh,
there are different
yeah,
dimensions. Like
that
dimension.
is from the
Mm.
algebra. I have not done
That,
it myself, but the
that
relation
no,
is sorry, yes, sir.
no, no,
Dimension.
that is a derivation. वो करना होगा
Yeah.
थोड़ा.
So the solid angle subtended by the area, the half of it is the actual phase that the geometric is the geometric phase that is added.
Okay.
That you have
Hey,
to do.
Priyanuj, that is done in the manual, na?
I don't. I have my manual
जीवन
open.
उसका है क्या? तुम्हारे पास जीवन तेरे पास है वो?
Oh wait,
जीवन is there? Jeevan left it.
wait.
Jeevan is not there.
Do I
Okay.
have the angle?
That is standard, I think. Right? That two beta is that I think it's very standard. That
Yeah, I know.
subtended area is to be
I
that
know
I think is
it's
standard.
standard because someone did it once. I
Okay.
forgot, but I
हाँ,
personally haven't done it.
Doubt was, I
But it's
think, like,
standard, yeah.
it is standard. वो थोड़ा देख लो वो है.
Yeah, how like how is it related? Because each A, B, C, D is defined by your Q, U, and V, and each Q, U, and V has its own angles, and you know the solid angle. So I think it is easily like integrable for any arbitrary ABC, and from there I think you can get. But yeah, I've not done it, so I won't say more.
Yeah. I think we need to ये देखना होगा थोड़ा. I think we need to manual में है नहीं क्या? वो two beta. I
Wait,
think
No, sir,
actually
everything will come from the Jones metric formulation. Everything will
Jones
come.
matrix. No, no, but solid angle may not be there, na?
Yeah,
Vishwajit.
no. You will get that 2 beta thing there. Solid
हाँ,
angle
हाँ,
will be
हाँ.
4 beta.
Actually, yeah,
May not be
yeah,
there.
Anirudh,
4
see,
beta, yeah.
obviously, see, there are
That
two
is there.
rotations, ना? वो
Hmm.
दो बार बीटा आता है ना, so e to the i beta, e to the i beta, e to the 2 i beta आ जाएगा उधर से.
Yes,
Yeah,
so
so
that is
that is
from
twice
there.
beta, but in the Poincare sphere, the solid angle will be 4 beta then.
4
हाँ,
beta,
हाँ,
yes.
हाँ. Oh,
Because
हाँ.
rotation in this plane is rotation of theta in this
हाँ,
plane
हाँ,
will
हाँ.
corresponding to theta rotation in point there. Yes.
Correct. That
yeah,
is very true.
conceptually, I had gotten it. I was just like mathematically, how are we?
Mathematically, you can do that from rotation matrix.
Yeah, yeah.
I think,
Do
I
the
think
rotation
Anirudh,
matrix and you will get for only theta.
वो actually
It
Muller
rotates
matrix
up.
में वो 2 alpha हो जाता है ना? That I
You will
just
get
wrote ना? वो 2 alpha हो जाता है. So when you rotate theta in Jones, Muller में it
exactly.
becomes 2
You will
theta.
get
So वो अगर तुम you put that t minus 1 t inverse rotation t, you will get 2 theta आ जाता है वो.
Like initially, I just had a dimensional problem कि solid angle and angle
हाँ
are.
वो तो एक 1D में एक 2D. हाँ, that is correct. But I
Like
think that is
conceptually, I had gotten it, but
Mhm.
just
Okay.
dimensionally, I was looking at it.
Okay, good discussion. So I think acha, are we ready to do the density matrix to this thing? Some discussion? Because I am slightly see because in density matrix formalism we always take that off diagonal terms as decoherence. Have you guys, by the way, have you guys done this, by the way? Have you done it in class? Density matrix? Huh? Have you done?
So we did density matrix in quantum mechanics, but nothing related to coherency matrix.
No, coherence matrix अभी किया. No, but pure state
We
mixed state density matrix वो
didn't
किया
touch
था.
decoherency, I think. I
Huh?
remember correctly. We didn't
No,
touch
so
decoherency. But we
so
did like
did you do
density
that
matrix
mixed state
testing.
density matrix? Wo off diagonal terms means what those mean and all that. So for pure state you only have diagonal terms, but for
Yeah.
mixed state you have those of वो किया था क्या?
Someone
Can,
talked.
can we do a discussion? I don't want to do it. You guys just like we did in the Drude model. Do you think you can do it on Friday? Tell me then. Okay, I'll not extend this class. Just tell me that if you can do it on Friday. I think it's very interesting if you can do that density matrix versus coherency matrix comparison. I thought you have done it, no? But I think that is covered. You
Sir,
have done some advanced quantum mechanics also, right? Or
yes, sir, we did mixed state and pure state in quantum mechanics too.
so karo na, फिर let us have the discussion then. But whatever, you're up to you because I think it is useful to draw these things and basically see I'll exactly frame the problem. So we are saying in quantum mechanics the mixed state basically means those off diagonal terms are a measure of the decoherence. Okay. Now coherency matrix mein, it is not necessary that the off diagonal terms tell you that there is no polarization. It is not that. It is just that the determinant has to be 0. So when you take AB minus CD, they are the same as the product of the diagonal terms. So how do you relate the coherence of a system? Is there, or rather, is there a relationship between the coherence of a system to the fact that polarization will be perfectly polarized in case the system is perfectly coherent as well? You see that? Can we somehow relate the coherency, the density matrix may the presence of the off diagonal terms to depolarization in the coherency matrix? That is my question to you. So if you think you can address this question, then we can. Is the question clear? Can we relate the off diagonal terms of the coherency matrix to depolarization, just like we related the off diagonal terms of the density matrix to decoherence? How can we relate that? Okay. So if we can sort of, if you think that we can draw parallels to density matrix, then we can meet on Friday for the discussion. Up to you. Okay, and again I will ask you to maybe make, yeah, this one is a I mean, dividing it into 5-6 groups probably doesn't make sense, but I think it's best if you guys discuss and make 2-3 presentations among yourselves and just tell us, because I'm giving you 4 days time. Okay, so tell me if you want to do this discussion. Acha, next class we will start something completely different, that is the ray tracing things. Very different, but very important and very useful, because that allows you to understand and to design how light sort of interacts with optical elements, and finally how you actually make resonators. That is very crucial in even making lasers and all that. Okay, ठीक है? Okay, so then let us meet tomorrow.